GKW Physics. I'm Mr. McConnelly, and today we're going to talk about the work energy theorem. And I've written three equations on the board. Kinetic energy is 1/2 mv squared. This is an equation that I'll go, it's in the reference table, but I'm going to go through it very quickly because pretty much everyone in this room has already learned it. And what it says is that the kinetic energy of an object is equal to 1/2 the mass in kilograms times the velocity squared, and velocity is in meters per second. This is kinetic energy. And energy, as you may recall from other years, is in joules. So you say there's joules, you have a certain number of joules of energy. Now the basic thing you have to understand about the kinetic energy equation is that it applies to things that are in motion. So when you have a mass in motion, you have kinetic energy. The next equation is the potential energy equation. And again, I'm going to kind of brush through it quickly because everyone has learned it before. But this is potential energy, which is also in joules. We have mass in kilograms. We have g, which is the acceleration of gravity, or negative 9.81 meters per second squared, as it always has been. And h is a height in meters. Now this equation usually applies when things are not moving. However, these things have to be elevated from the surface of the Earth, or they have to be allowed to fall and be accelerated on by gravity. So if you're holding this controller above the table and you drop it, gravity can pull it down, so this equation can apply, and the height would be based on how far it is from the surface of the table. If you're dropping something over here, it's going to fall all the way down and hit the floor. The height is based on the distance from the floor. So this is potential energy. So it's the energy that will happen if you let something go with mass. And this is kinetic energy, the energy when something's moving. Now, the last one is work. We've already done this. I'm not going to label it again. Work is force times distance. But I want to take this in a little bit different direction today. And what I want to do is kind of show you how two of these equations are actually equal to one another. So, we know that force is mass times acceleration. So if I take and plug that into our work equation, I would get something like mass times acceleration times distance, or mass. Now, if I take it a little bit further here, what I can also do is I can go think about an old equation, Vf squared equals Vi squared plus 2AD. And I'm going to solve for d in this case. So I got Vf squared minus Vi squared over 2A is equal to d. But I'm going to eliminate one more thing. The initial velocity, because we're going to be basically dropping an object, the initial velocity when you're holding something up in the air and you're going to drop it is a 0, so that's going to go away. So it's really going to be Vf squared over 2A equals d. And I'm going to bring that back over and plug it in right there. So I got W equals m times A. And then in this part right here, I'm going to plug in Vf squared over 2A. And it seems to me I kind of have a mess. But it's not so bad. Watch this. The accelerations cancel out because there's one on the top and there's one on the bottom. If you have a look at this right here, you could really make this a 1/2 in m in the Vf squared, because you can pull out the number, right? You can pull out the 1/2. And now things are starting to look a little bit vaguely familiar, I would say. Because if you look at this, and then you look at this, what are you seeing? They're both 1/2 mv squared. And what I've proven to you, hopefully, that's my goal, what I've proven to you is that the work equation is equal to the kinetic energy equation. That's useful. So, now if you spin your attention over this way, I have a bowling ball here. And the bowling ball works well to show things because everyone knows that a bowling ball is pretty massive. And you realize this thing, if I'm holding it out in front of me, second equation, if I'm holding it out in front of me, it has potential energy. Quite a bit, because it's got quite a bit of mass. If I drop it, shoot, and it hits the floor, it's going to have quite a bit of kinetic energy, because as soon as I let it go, that mass is going to suck it right down to the floor, and you're going to have quite a bit of kinetic energy. And you also know that if I'm picking this bowling ball up, I have to do quite a bit of work, because it's got quite a bit of mass, it's got quite a bit of force. I lift it up, so I'm going to do work. But here's what you might not know, or you might not understand. Start from the bottom. If this thing's sitting on the floor, its height is 0, it's got no potential energy. It's just sitting there. Now, as I pick it up, I do work. Let's say the number is 10 joules of work. So it took 10 joules of work to pick it up. Once I'm up here, I'm not moving anymore, I'm not doing any work. However, now I have potential energy. How much potential energy do you think I have? 10 joules. If I did 10 joules of work to pick it up, I now have 10 joules of potential energy, and we can calculate it out with the equation. Now if I get all fumbly and I drop the thing, and it falls down, right 1 nanomillimeter before it hits the floor, how much kinetic energy do you think it has? 10 joules. So the 10 joules of work that it took to pick it up turns into 10 joules of potential energy. You drop it, you got 10 joules of kinetic right before it hits the floor. And that is called the work-energy theorem, physics.